is a disjunction of literals. A literal is a proposition or negation of the proposition. These are all definitions. Okay? So, if I can somehow magically assume that everything I know can be written in this form, everything is clauses. The length doesn't matter. I just considered two length clauses. Okay? In fact, the last time you saw a clause was in the Boolean satisfiability definition. Those were clauses. By the way, those were disjunctive clauses. Okay? And it turns out, in a minute we'll point out, that any random propositional logic knowledge base can be converted in polynomial time into a set of clauses of this type. And it's meaning conserving. That means the clauses, the conjunction of clauses is true exactly in the same words where the original knowledge base is true. So until I show that to you, you take my word that it will be shown. Now if that is the case, then I have alpha or beta, not beta or gamma, let's say, as two of the sentences. Then what I get to do is sort of symbolically cancel beta and not beta and write alpha or gamma. This is proposition rule. This is the resolution rule of inference. First of all, you can prove to yourself that this is sound. You can do alpha, beta, gamma. There are 8-row table. In the 8-row table, you consider the rows where this and this together are true, and realize that this will also be true exact. In those rows, this will also be true. You see what I'm saying? Do it yourself. Then you have proved soundness of resolution inference. You have something to be proud of. Then you say, you didn't get me. I know soundness proofs already. Show me completeness. And I'll hand wave and say, read the text. Because completeness requires an induction proof. Okay? And the textbook nicely provides an induction proof showing that, in fact, by mathematical induction, they show that everything that is attained is derived by this rule. So proving completeness is actually hard. Okay? But it turns out that it is in fact true. And for sure, if I go back to my old example, this one, I'll check if this will be solvable. This one, is this solvable? Right? That's the one that was given as trouble. So I'll first write them. So basically, first of all, if Will goes, Jane will go, I write this as not W or J. In fact, basically, this was written as W implies J, but you should remember A implies B is identically equal to not A or B. Anytime you sort of start having delusions, thinking implication is causality, nobody thinks R is causality. Right? Implication looks like causality. They put a nice little direction, they sometimes actually use an arrow, and juniors are confused. But the same reason why juniors will be confused in the base nets, because we put arrows, and you think A is causing B. Nah, it's not. We're just catching you, But in fact, there is no causality there either. Okay? So if in fact A implies B is identically equal to not A or B. That's the definition, essentially. So now I did tell you that anything can be written in my format, and it is in fact true. W or J, W implies J can be written as W or J. And then if Will doesn't go, then Jane will still go. That basically means not W implies J, which will be not of not W or J, which is W or J. I want to check, will Jane go? So I take this, I cancel out W and W, I get J or J. And I hoodwink and say J or J is J. And so I proved. if I do it this way, I say forward resolution theorem proving. But then you would be right in saying you cheated. You said you'll only use this rule and nothing else. And this additional rule, JRJ is J, that was an extra rule. We agree that it's true, but you're not supposed to use another rule. You're only supposed to use one rule. Right? I mean, he seems to be a happy enough guy. But people are crazy. People say, no, you cheated. So it turns out, actually, there is a different way of using resolution, which is essentially just like model theory used in two ways, right? One is you check the rows where the knowledge base is true and made sure that alpha is true in those rows. The other is you constructed a new column which said KB and not alpha and said it is unsatisfiable. So for resolution 2, you can have what is called resolution refutation method. And this is actually how people do theorem proving. This is how Prolog more or less works. Okay? What resolution theorem proving, resolution refutation says is that you want to prove J, let's just take negation of J, not J, add it to the knowledge base. Now I have not W or J, and W or J, and not J. I need to be able to do something such that I basically say, kaboom happened, right? Basically, if I add the negation of what I'm trying to prove, in the model theoretic sense, it should be unsatisfiable. In proof theoretic sense, you should get false. What is false as a clause? Did you understand what I said? What is false as a clausal form? Empty clause. Empty clause. False is empty clause. So if I do this and I do a bunch of resolutions, I get an empty clause. Everything gets cancelled out, I get an empty clause. Then I say, I'm done. I derived false from what you know. Which means in the model theoretic sense, I have shown KB and not alpha is unsatisfiable. Which means alpha must have been satisfiable. Or KB was actually inconsistent. In which case alpha is anyway satisfiable. Did you understand what I'm just saying? So if the knowledge base is inconsistent, everything is proved. If the knowledge base is not inconsistent, this proof still says that you're able to prove it. So that's basically, resolution refutation is also called mad chase for empty clause. Mad chase for empty clause. Okay? Now here there is not much of a chase. So tell me what happens. Now what can I do? Like I can do, let's say this, let's say I can do this and this. Right? Normally when you do the resolution, you kind of put line like this, and not J and J cancels out, and I get to write not W. Not W and W and not J. This and this cancels out, I get to write J. This and this. Am I cheating because I use this poor guy not J multiple times? If a fact is used more than once in your life, does the fact lose its factiness? You see what I'm saying? It's not like somebody says, here's a fact, use it carefully only 2 times in your life. There is no such thing. So what I did is completely legit. And I did get an empty clause, which basically made you extremely happy, because you proved a theorem. Just when you're feeling happy, I want to show you how this can, I can show you later, I'll come back to this next class, but I want to show, I'll come back to this slide next class, that anything at all can be converted into clausal form. That's not that hard, but it can be shown. You kind of can see that A implies B can be not A or B. And then if you use those kinds of things as well as distribution of disjunctions over conjunctions, then you can eventually convert everything into a conjunction of disjunctions. I can give you a little thing, that's the set of rules there. But what I want you to do is to tell you theorem proving is hard. And there basically, this is my most animated slide for the day. And I'll just tell you, search is hard in the sense there's a large number of resolutions I will do such that in the end I'll get an empty class. Now, I happen to know what to do such that I can get to an empty class. But what your program will do is it doesn't know how to go to the empty class. It'll take any arbitrary set of classes and tries to resolve them. And sees whenever I get an empty class, I'm done. Otherwise, I'll keep on doing this. What we are doing here is a search. And I'll show you one path for this slightly hard problem. And then you get to go home. Okay, it's a very simple problem. If the grass is wet, then it is either raining or the sprinkler is on. If it's raining, then Timmy is happy. If sprinklers are on, then Timmy is happy. If Timmy is happy, then Timmy sings. Timmy is not singing. Prove that the grass is not wet. I mean, this is a world-saving kind of a problem, right? Okay, so I'm going to do it the way I told you I'll do, okay? So those are basically just direct writing English into logical form. So I just made up some proposition names. GW is grass is wet, okay? And R is raining, SP is sprinkler. TH is Timmy is happy, SG is Timmy singing, and so then this becomes GWR implies R or SP, R implies TH, SP implies TH, TH implies SG, not SG is also true, and I want to prove, entail is, I want to prove not GW. Can you entail not GW? Okay? Prove that the grass is not wet, right? And then what I want to do then is convert all of these guys into clausal form. It turns out it's very simple because all the implications just very easily can be converted to clausal form. I need to convert this guy into clausal form too, but before that I first negate what I'm trying to prove and then convert it into clausal form. Important. You take the theorem that you're trying to prove, negate it, then convert it into the clausal form. So I want to prove not GW. So then refutation of that is not of not GW, which is GW, which I need to convert to causal form. It's already in the causal form. So you can see a bunch of things can be connected together. This and this can be resolved. You get an RTH, and this can be resolved, and I get not SB and SG, not SB and SG. Not every resolution reduces the clause length. Some resolutions actually can increase the clause length. Suppose I have a 5-length clause and a 7-length clause. At the end of this clause is P. At the end of this clause is not P. P and not P can be resolved. I got 4 plus 6, 10-length clause now. That's going in the wrong direction as far as empty clause is concerned. Do you see what I'm saying? Okay, heuristically you're going in the wrong direction. You want to become smaller. In general, the heuristic is to make the clauses from the resolution be smaller. Okay, so this is the mind-bending thing. I'll just show a couple of resolutions and then magically the empty clause occurs. You can check every one of the resolutions is correct. The question is, how did you know these are the correct set of resolutions? And I'll say, well, I won't. You just are supposed to write a search problem and use some variation of search algorithms that you know. Everything is search eventually. Okay, so there, RSP. And so notice that anything that I derive can be used. Once I derive, it's a fact. It can be used with other facts. Okay, then I get that, then I get that, I get that, I get that, I get that. Okay, class. Right? Done. I showed an empty class. Okay? Now, obviously, under time pressure, in midterm, on the final, people see empty classes everywhere. Right? There are lots and lots of ways people see empty classes. P or Q, not P or not Q. What the heck? Yeah, it's going to cancel this, cancel this, empty class. Done. Bosoness. In fact, this is not sound. This is not sound. Don't do it. Okay? Because you only get to resolve on one literal. You only get to resolve on one literal. If there is an empty class, what that means is there is no world where both of them can be true. That's what it means. If you have like a class P and another class not P, then you get P and not P go away, you get an empty class. That's because there is no world where both P is true and not P is true. What you're saying here is there is no world where P or Q is true and not P or not Q is true. Is that true? No. So you just made a empty class on demand, under time pressure. You don't get to do that. So next class when we come back, we'll essentially basically show that these are all essentially search algorithms, and you can use your ideas of search to organize the search tree. And that would have basically done the position.